So we'll start with a team activity where a group of 3 people will work together. So I will give you a template like this. You'll be collecting some data using dice. When you use 2 dice, let's say you get 1 and 3. Then you find the average, like 1 plus 3 by 2. And put that average here. Repeat that second time, third time, fourth time. So this is up to 15. And then come to average with 3 dice. You get the scores, let's say 5, 7. No, you cannot get 7, it's a dice, so only 6. So 5, 6, and maybe 3. You add them, divide by 3, you get average. So put that average here. So repeat with 3 and repeat with 5. And then you make histograms. So basically you will have 3 histograms, one below the other. So make your teams and then take one each. So once you are finished with your full names, not nicknames, full names so that I know the participation. So you take a picture and upload on the course website. I will let you know where to upload. Before we proceed with the lecture, I received this sample product from a company called Ridge. So this is basically a wallet. It can hold up to 12 cards. You push from this side, your card comes out. It came in this box. And it also includes this tool basically to customize RFID blocking modular design. And they also shared with me a unique code that I will provide in the description area below this video. You can use that to get 10% discount on these interesting wallets. These are getting very popular. Let's continue with the lecture. So this is one of the teams. Another team and 3 different plots. So there are basically like 3 things we look for when we look at a histogram. One is the location, where most of the values are concentrated. Second, we look for how much is the spread or the variability, like how far spread they are. And the third thing we look for is shape, like what is the pattern. It is like exponential or normal or uniform, like almost more or less same. So what do you observe, especially when you go from like plot 1 to 2 to 3, anything that you feel is going on. For 2, the spread you are saying is more, and for with 5 and 3, maybe more values in the middle, concentrated in the middle. There is some concentration here also, but as you correctly pointed out, spread is also more. So the key point, like why we did this exercise is, whatever you observe here, that variability coming down and then more concentration in the middle, taking shape as we move up. So that's what is called Central Limit Theorem. We'll open a new file for chapter 7. So we'll say save as. And I will clean this up, clean this up, clean this up. So chapter 7 is our latest file. Central Limit Theorem. And for this, I will make use of a library that will need a package called TeachingDemos. Let me first install it. After installing any package, so that's a one-time activity. After installing it, don't forget to run library line. Many people miss that. So TeachingDemos and run the line. So we'll use clt.example. As I start typing CLT, Central Limit Theorem, this pops up. So if I say 1, basically it is going to draw some histograms. So if I say 1, what it means is, you can think of the dice. You are taking one dice and just rolling it. So you get a number, you record that, second dice, note a number, and then create a histogram. And immediately what it does is, by default, it creates 4 different histograms. It says sample size is 1, and this is the first histogram where it has taken a random sample from a normal distribution many times and then created a histogram. So because the sample came from normal distribution, it is looking like this. It will look normal distribution. Similarly, uniform distribution, something like dice. If your sample size is only 1, you are not taking average, but only 1. So 1 is equally likely, 2 is equally likely, 3, 4, 5, 6. You get those values almost like this. Uniform kind of curve. And then there's a gamma distribution similar to like exponential, right skewed. And then there's another distribution called beta, which is like a bath-shaped curve. So high values at the beginning and at the end, and low values in the middle. So it has taken sample from those 4 distributions, just one sample, and created histogram, and they will look like from whatever that sample is coming from. If it is coming from normal, your histogram will look like normal. If it is coming from uniform, it will look like uniform. So now I will change this 1 to 2. So your first column where you got averages of 2 values. So if I do that, so what it means is, it will draw 2 samples from normal distribution, find the average, again 2 samples, find the average, do it for more than maybe 50 or 100 times, and then create a histogram. Same thing, it will take 2 samples from uniform distribution, find the average, again repeat that. We did it 15 times, it may do like 100 times. If we do 2, notice what happens to the shapes of these. Now when we take a sample of size 2 and plot the averages, normal distribution will still look like normal, but look at this highly right skewed distribution suddenly changes little bit. This was uniform, and it starts to look like a normal distribution. And this was like very different, and it is again changing its shape. If I go up to 5, so do you notice what is happening with the distributions? As I increase the sample size and plot the averages, not individual values, but averages, what is happening to 4 very different distributions? What is happening with them? They are becoming similar to which distribution? Which one? Normal distribution. Because in the class we could not do more than 5, it would have taken a lot of time. But I can do 30, for example, very easily here. So what we are doing, like you can think of like 30 dice rolling at once, noting down all the numbers and then finding average and plotting those averages. So if you do that, you can see that whatever was the initial distribution, that totally changes by the time you are plotting averages based on sample of size 30. They all become normal distribution. So that's what is the central limit theorem. Just like Pythagoras theorem in mathematics, that's very important if you are studying geometry. In statistics, central limit theorem is the most important theorem, and basically it highlights the importance of normal distribution. So it allows normal distribution to be used in so many variety of situations, because it shows that when you have sufficient sample size, almost any distribution you start with, if you plot the averages, you end up with a normal distribution. So it makes calculations much easier because gamma distribution or beta, like calculations are not that easy. Statistics class usually, so some people enjoy and some people find it difficult. And when I think about it, like why some people find it difficult, one reason like I can think of is, let's say somebody was studying history in middle school or high school and missed some classes and then comes back because of sickness or something and comes back to the class, they can catch up very easily. Or miss some lectures in classes in English. They come back and then they can pick up very quickly. But if they miss like geometry class, they missed a class on Pythagoras theorem, they will not be able to understand geometry for the rest of their life if that's not clear to them. Similarly in statistics, why people have difficulty, because if they miss some part, it's not that next class you come and then you don't know what is normal distribution and still you can work on those problems. So that cannot happen. So one needs some kind of continuity and also like understanding of some important concepts. So central limit theorem basically is like that. It is basically telling normal distribution is the most important distribution in statistics. Now if you think of why like we are taking samples so many times. When you take a sample and you say that this is a representative sample and you want to figure out what is going on in the population, so that's just one sample. There are so many samples possible, like you got 15 different samples to get the average in the first column. Similarly for the second column you had 15 different samples from the same 6 or maybe 3 dice. How many ways, for example, how many ways or how many unique random samples are possible if I want 5 samples out of, let's say, 600. Suppose I have like 600 as a population, how many samples of 5 can I take? So if you recall, earlier we had done that calculation using choose. Number of unique samples, 5 out of 600. Suppose I want to figure this out, in how many ways I can get 5 samples. Then the function that we use is choose 605. So that's a very big number. Maybe 637 billion. So more than 600 billion ways you can get 5 out of 600. If I have a test bank, for example, of questions, 100 questions, and for some quiz I want to select 5, so how many ways I can get 5 out of 100? I can use this function choose 105. So more than 75 million ways I can get 5 out of 100. I don't need a class of like 75 million to give them unique set of questions. With the 5 out of 100, you have so many possible combinations. But when you are getting a sample, you are getting just 1 out of that many. You are getting just 1 out of that many. We want to get an idea like not just about that sample, but also like the entire population, so that we can make a good judgment. Basically, central limit theorem helps to study all those things. If your initial distribution is, let's say, uniform, some random variable x, or if your initial distribution is maybe right skewed, or maybe left skewed, or maybe irregular, like 2 peaks, or whatever may be the shape. So all these, it doesn't matter what is the initial shape of random variable x. all these under some situation will become normal distribution. So this is not x but x bar. So x-axis is x bar values, like average of 2 dice or 3 dice or 5 dice. So we are finding averages and then plotting them. So the values are for averages. So in that sense, what you have in the middle is not average but average of averages. So I'm putting 2 bar, which means that middle value is average of averages. So under some conditions, you end up with this normal distribution, and the condition is very simple. You need to have sufficient sample size. So if you have a sample size of more than 30 and you keep on finding averages, like we had sample size of 2 and then 3 and then 5, but if the sample size is 30 or more, then it doesn't matter what was the initial shape. All end up in the normal distribution. The only thing is you have average of, like average in the middle, and then the standard deviation, we can say sigma of x bar is equal to standard deviation of individual distributions divided by square root of n. This sigma of x bar is called standard error. We use a different term from standard deviation. It is standard deviation of the distribution of x bars, but it is called standard error. We don't call it standard deviation, but we call it standard error, which means it is standard deviation of the means. Once you have that, so this is central limit theorem, but once you have that, once you have the normal distribution, then whatever you did in the last chapter, everything remains same. Any calculation that you want to make, any probability that you want to find, you'll be finding with this mean, and not sigma, but divided by square root of n. That square root of n also means, because it is in the denominator, as the sample size increases, the variability of this distribution will come down. And that you mentioned actually in those plots, that the first plot has more variability and third plot has less variability. So that was because n is in the denominator. So when n goes up, the standard error will go down. Let's look at one example. A manufacturer produces 25-pound lifting weights. Lowest actual weight is 24 pounds, highest is 26. Each weight is equally likely, so the distribution of weights is uniform. And then a sample of 100 weights is taken. What is the distribution for weights of 25-pound lifting weight? X follows uniform distribution with those two parameters A and B. So A was 24 and B was 26. In one, it also says what is the mean and standard deviation. So whatever is the mean and standard deviation for uniform distribution, that's not going to change. Or x bar for uniform distribution is A plus B by 2. So A is 24, B is 26 by 2, so 25 pounds. And then standard deviation. So standard deviation, if you recall, I had given this formula, B minus A whole square divided by 12 and square root of that. So if you plug in the values, B is 26, A is 24 whole square by 12. So 2 square is 4. So 4 by 12, square root of 1 by 3. If you simplify, you should get 0.5774. What is the distribution for the mean weight of 100 25-pound lifting weights? So uniform will become what distribution? If your you are taking average of 100 values. Which distribution? Normal? Normal. So that's the central limit theorem. I will make this picture for x bar. So average is not going to change. Average is 25 pounds. So that remains 25. Sigma of x bar is the standard deviation of individual values divided by square root of n. You calculated standard deviation. So let me write down, this is s divided by square root of n. 0.5774. And then square root of n. How much is n? 100. Basically it becomes 10. So 0.05774. Distribution of x bars will be normal with mean 25 and standard deviation 0.05774. So that's the only extra thing we have to do. We have to figure out the standard error or standard deviation of x bar. So we have to divide that s by square root of n. That's the only extra step. Mean doesn't change. Mean is still in the middle. The only thing that changes is the variability. Part C says, find the probability that mean actual weight for the 100 weights is less than 24.9. So the question is being asked in terms of mean. If they were asking a question for individual values, we use uniform distribution. But the question is about mean, so we have to use normal distribution. C will be, so this is 25 and sigma of x bar is 0.05774 and 24.9 is somewhere here, and we want this area. We use our probability for normal distribution formula. This value is 24.9, mean is 25, and this is 0.05774.